just to show the transistor count, right? We keep increasing the transistor count, just use the not scaling, but no, as what you all have said or we just discussed, is the death of the Moore's law if you want to keep going up, right? But we do have more transistors because we put many chiplets together. We're still scaling them exponentially. Now, then what happened? Why we suddenly stop? That one of them is so-called memory power law. It here show the year, right? And now let's look at the transistor. While transistor keep going up, that's nice, right? But the performance actually slows down. Why? Because we did not increase the frequency. The reason is very simple. It is too hot. Look at the power it generates, 100 watts. Some of them go to 200, 300 watts per chip. It's really hot, right? When I just joined the PhD program, I took a class in this. They show us the video. They can use the chip at that time to cook an egg, right? They just want to show us that, hey, this is the end of the world, right? The chip is cooking the egg. And a few years later, the temperature is going to higher than the rocket's nozzle. And 10 years later, it will be higher than the sun's surface temperature. This is the end, right? So that's why we don't increase the frequency anymore. That's why I emphasize in this slide, you don't see a very good improvement. That's not because of technology. If you really want 10 gigahertz, it's not a problem. That is just because of the power, right? Because power, we will discuss more later, related to the frequency, is proportional to the frequency, right? Higher frequency, you have more dynamic power. You keep switching. But we are not stupid. Intel, they use multi-core, right? If one transistor cannot run so fast, then I just use multi-core. So now this is related to the throughput instead of just latency that I discussed earlier. As long as you can finish this computation for me today, that is fine, right? I don't care how slow you are, how many core you are using. And now if you go to multi-core, you have to think about many things. How do they connect them together? How do you distribute the job evenly, etc.? Okay. Here shows the trend in the transistor density for the recent one, right? For 45 nanometer and then to 14 and 10 nanometer, right? They keep still trying to increase, but we don't only rely on the transistor nowadays, right? So I think I'm a little bit slow. I actually really want to go to a few slides before we end. So today, what is the challenge? How do we further improve the performance, right? Well, you cannot just make the transistor smaller and smaller. That is because the parasitic is affecting us. In the past, the transistor is the slowest part. But now the parasitic RC, capacitance and resistance, or the interconnect is actually making it very slow, okay? Power consumption is a big deal, right? If I have 1 nanoampere of leakage, what do you think per transistor? That's very small. But you just told me that we have 1 billion transistors. Then what, or even 10 billion, right? Let's make it more exaggerating. Then I have 10 ampere. It means that you turn on off your transistor in your CPU, it keeps leaking 10 ampere, which is about 10 watts of power. That's not acceptable, right? So how do you do that? You need to be innovative. How do you turn on and turn off different blocks? We are going to discuss this a little bit in this class, right? How do you improve the area efficiency? Right, we can use stack nanowire or nanosheet, right? And how do you design it? If you want to stack the transistor together, you cannot use the regular EDA tool. That's why DARPA, they have an electronic resurgence initiative in 2017 to help the EDA company to improve it, right? Besides that, you need to think about reliability. Right now, we operate at lower voltage so that we have less power consumption. Right, low voltage means that you are more susceptible to the noise. Right, and also you will degrade over time. How do you deal with that? Because now you're operating at lower voltage. If it degrades, it has a big impact. Okay, and also radiation effect and variability. Let me just tell you what is variability, right? But we will not learn this here, but these are very important, unfortunately. So I hope that you will bear this in mind. Okay, it will be good for a job interview. Here shows a variability. Even the VT can change. Look at this channel length. When I change the channel length, make it smaller and smaller, VTH will change so much when I just change a little bit. You know, fabrication is impossible to make them exactly the same. Then if just a little bit variation, you change the VT so much, your inverter is not going to work. And same for the leakage. When you are too small due to short channel effect, what you just said, I have a lot of leakage. So you need to design for this also. However, we are not going to discuss this in detail, but I hope you can bear this in mind, okay? I'm going to show you how the technology goes, right? Here, I show you one of the most recent one. This is a very recent paper just 2 months ago in IEDM. This is one of the most important conference in my area. Now, they are talking about 3 nanometer, 2 nanometer, 1.5 nanometer. Do you know what is 3 nanometer? It is not the gate length. Last time I asked you, what is that? It's no longer the gate length. It's just the technology node. In 3 nanometer, the transistor gate length, I forgot what it is, but I think it's about 40 nanometer. Okay, it's not even 3 nanometer. But however, they dare to say that we're scaling in the 3 nanometer because it's giving the performance improvement, like the Moore's law, that we have maybe 1.2x improvement over 5 nanometer. Okay, same for 5 nanometer. It is not the it's not about the gate length. Okay. So what's so special? The first one is FinFET. Anyone can explain to me what is FinFET? Which has been used already in Intel, right? Since 40 nanometer technology node for many years. And I think your computer has billions of FinFET already if you bought it recently. Anyone know what is FinFET?
Professor, it's a 3D transistor where it has three dimensions, and the gate is controlled in 2 directions.
Very good. So it is like this, right? I think although this is not the goal of our class, but everyone should know that if you want to go out to find a job and say that you know about device or high-speed digital. This is a regular device. We call it planar device. This is the gate, this is the source, this is the drain, right? But then the gate is far away from the substrate. You can have a lot of leakage. So what can we do? If we can have a double gate controlling from the bottom, that would be great, but it's difficult to fabricate. What we do is, okay, we actually make a so-called 3D device. Like this. I'm trying to draw a 3D. And I remove the source part and drain part. So this is source, this is drain. The source is the current is flowing along this fin, just like the fin of a fish. And on top of it, then we wrap around, this is the gate. So you can imagine the gate is controlling the 2 parts or even 3 parts if you want, or the top, which is very thin, very small, right? And this is the cross-section of a FinFET. Do you see that? Right, so in 3 nanometer, definitely we need to use FinFET to have a very good channel control to reduce the leakage while keeping the same current. But when you go to 2 nanometer, you see this one, it becomes the so-called stacked nanowire. If you look at the cross-section of a FinFET, it is something like this, right? The current is going into the paper, right? This is the here I'm cutting the cross-section along here, then you get this. We can even say, hey, how about we do this? I make this nanowire and then the gate is surrounding that. I have many layers of that. That is the stacked nanowire. Okay, so you see here, the cross-section, they are all disconnected. The current is going inside. Okay, so why anyone just now, this student say that I have FinFET, I have the gate controlling 2 sides, so it has a better control. Can you explain to me why nanowire would be better than FinFET? or nanosheet? Any guess? Why now the gate is wrapping the whole device? Why would you? So do you? Please ask question, right? If you have anything, right? You ask now and you can answer in your interview. Isn't that great? And you can answer in the midterm. Anyone has idea? Yeah.
I'm not sure.
I just had a quick question with the stacked nanowire. So if these gates are all individual, wouldn't it cause like a lot heavy like wire strain, like having to wire each gate individually? Like I'm not understanding like how they're kind of connected or if they're supposed to be connected.
Very good. When I do this step, they are the same gate. They are all connected. They are the same. So it is just like this gate. It is just the same, but I break the film into many different parts. Do I answer your question?
I see. Okay, thank you.
Yeah. So this is one single transistor. Okay. It's not two transistor or three transistor.
So sorry to interrupt. So I just want to kind of re-clarify. So these squares, the inner square that you're drawing, those are basically the connection from source to drain, and the gates is kind of, the circle is basically this gate just kind of running on top of those.
Exactly. This is from source to, this is what we call the channel. This is the silicon.
Okay, thank you.
Yeah. And so you asked me question. Can you answer my question also, just in return? I'm just kidding. But do you have idea why this one is better than FinFET?
You have more gate control, right?
Oh, good. Why I have more gate control?
Compared to FinFET, you can, you have 3 sides for FinFET, but for, nanowire, you have 360 degrees all around.
You are right. Four sides, right? You just wrap it around. It's just like you are controlling the hose. Think about that. You can squeeze the hose from all directions, right? Assume that you are able to squeeze it, right? Actually, you cannot because you need to squeeze the plastic. But let's say you squeeze from all direction, right? The hose, which is a very flexible membrane, it is easier to just squeeze it from 2 sides. And it is easier than just squeeze from 1 side. That's how you control the leakage of the water, right? That's exactly what you do. Now.
So, Professor?
Yeah.
Can we say that source is isolated from drain in case of nanosheet than in FinFET?
They are still isolated. So what I'm trying to do is a cross section. So sorry for my bad drawing, right? If I try to look at the 3D view, it becomes this. If I try to do the 3D view, this is the wire. And then here I have the source, I have the drain.
Okay, got it.
Is that clear?
Yeah, thank you.
Okay, good. If not clear, let me know, right? So it is isolated electrically if your gate has negative bias, and they're connected if your gate has a positive bias. Okay. Now what you're seeing here, all the new technology, something called BPR. You don't know that. I only just know that recently. Okay, but probably you know that. I'm sorry. It's called buried power rail. Nowadays, in order to deliver the power from the chip to different transistor, what do we do? If you have any layout experience, you know that you are going to have a big metal wire on top of this and to deliver all the power. And then go to each standard cell, you need to wire it down to the lower metal and then deliver to that cell. That's a waste of real estate, right? So now people are trying to put the power rail under the silicon. You see the transistor on top. This is the transistor. And we put the power rail under, right? It's just like in the old time, all the power cable, they fly over our house, right? And now they all bury in the ground to save the area. This is very challenging technically, right? We don't talk about how to fabricate such device. They can do that. But the point is with this one, you see, I can make the power rail so thick it can be have very low resistance. It saves a lot of area, right? So this is something, a keyword you want to memorize for your interview. I think it makes sense, right? And besides this, we try to squeeze every centimeter, right? Every nanometer. Instead of separate NMOS, for example, this can be N type. I don't know which is N. This can be P type. Here we separate them. If you have done any layout, you see that I need to separate the N from P pretty far away to avoid them interference with each other during fabrication. So people come up with this Forksheet, just like a fork, right? But this is, and I need to tell you one thing. Nowadays, people actually don't want to do nanowire. They actually want to do nanosheet. You see this more because overall is on-off current trade-off is better. What is nanowire? Just a circle. What's nanosheet? It's just a very thin sheet. Again, you're surrounded by the gate. Okay, the cross section, right? Right, this is the silicon and this is the gate. Okay, so here you see that it's elongated rectangle, right? So it's a sheet. Again, the current going into the screen. Now this Forksheet is what? You put the device so close to each other. On the left is N type, on the P is P type. That improves the layout efficiency a lot. Just know that there's something like this. No worry about too much how to do that. Okay. Air gap now is really innovative. What is a capacitor? Capacitor is epsilon divided by T. If you want to reduce your delay of this wire, reduce the delay of the transistor, you want to have zero capacitance. You cannot do that. The best you can do is have a gap that is vacuum or air. I don't want to have silicon dioxide. I don't want to have nitride, which has high dielectric constant. So they use the fabrication. Actually, in the most modern chip, there are lots of gap, right? You think that this is wonderful? And then you will say, how about reliability, man? How can we prevent the water moisture to go in? And how can we prevent it from collapsing during fabrication? And even if it doesn't collapse, it will reduce the yield, right? Because it's less rigid, right? But this is what we are doing nowadays. We try to add the air gap at the right place to reduce the capacitance. And this is not enough. When we go to 1.5 nanometer technology, the goal is that I am going to stack the N type or P type, let's say this is P or N, on top of each other. If some of you have experience of doing SRAM layout, you know that I have 60 SRAM. Well, what if I put the two PMOS on top? I save a lot of area, right? That is Moore's law. In the past, we cannot do that. Now the technology is so good. I can just, in the next technology, I do nothing, but just move the P to the top. Then I can increase the, let's say the area by 4 times. I mean, the density by 4 times for the same area. And that is so-called complementary FET. How do we grow it? You can do the so-called monolithic integration, very expensive and very difficult. How can I grow the PMOS without affecting the NMOS? Or wafer bonding, sequential integration. You grow on one wafer with N type, another with P type, then you align it so well. I put them together, it becomes an SRAM cell, right? You see that I cannot have more than 5 nanometer, 2 nanometer misalignment for the whole die, right? And how about in the future? In the future is we don't use silicon. We use something called 2D material. Two-dimensional material, for example, molybdenum disulfide. All these things has high mobility and they are just single layer. So you don't have variability problem. Okay, so why I want to say this to you, or I want to just tell you that so many things are going on. Bury power rail to save your area, Forksheet to make the MP so close, air gap here to reduce the capacitance. You see this metal too, Now the metal to metal coupling will be 4 times lower compared to the silicon dioxide, and 2-dimensional channel material. That will be the future, right? So what you're going to learn in this class, unfortunately, I tell you, is all old stuff, right? But they are just the multiplication and addition that you need to learn. And of course, it's not really old, because nowadays the most profitable technology node is still 65 nanometer, 90 nanometer, because they're so mature, you don't have to pay much, and then it can satisfy a lot of the requirement. So why don't you use this, right? But in the future, if you have a chance to work with this advanced material, you need to change your mindset. Many things will be different, okay? I spent a lot of time, but I think it is worthy. Any questions about this picture? And I forgot to tell you, this is the pitch, PP, the poly to poly pitch. How far the poly away? You see when I talk about 3 nanometer, the pitch is still 44 nanometer. Metal pitch is 21 nanometer. It basically means from one metal to another, the periodic, right? So your metal width may be 10 nanometer, very small already, actually, right? This one may be talking about metal width of 5 nanometer or 6 nanometer. This is very small. It's difficult to print. Okay, so if no more question, another thing I want to tell you, right? Again, you may think I'm wasting your time, but I do want you to know this. Nowadays, we talk about making the chip good, but at the same time, packaging is very important. We all talk about system on chip, but system on chip nowadays is very simple, right? Or those we already learned, right? So we are going to do 3D packaging, what we call system in package. In the same system, I put my DRAM, my logic, or even one SoC on top of another SoC, right? And how are they connected? They connect through something called silicon interposer. This is basically nothing but just the silicon wafer itself. So on this silicon die, they make a lot of pattern for efficient communication between 2 die. Now, we talk about Moore's law, we say it's dead, right? Because we cannot squeeze more, make it more smaller squeeze, higher density. But now I use silicon interposer and put 2 together, and if they can communicate as fast as before, then isn't that I am extending the Moore's law? And now look at this pitch density. It's talking about 1 billion, right? Or 0.1 billion per mm square. Or the pitch talking about 100 nanometer. It's still not very small, but it's very dense. So their speed is also very fast, right? And then we will do die stacking through the so-called microbond, right? And to stack them, we can do wafer to wafer bonding, to 2 wafer, the whole wafer, 12-inch wafer, bond to a 12-inch wafer. Then you're done. You have 1,000 die on your wafer, then you are done with all this, right? But what if some die fail, right? The fail one connected to the good one, then the system is useless, right? So you can also do die to wafer or die to die, okay? Another is wafer to wafer sequential processing, right? You just, again, after you put on the wafer, and then you continue to do the process, and even do the transistor to transistor stacking. So nowadays, all the things 20 years old or 30 years ago that is forbidden in the fab, or you'll be laughed by people, say that you are crazy, you are dreaming, you are not expert, are being realized, right? Many years ago, they say, no, you cannot have copper in the fab, right? Nowadays, we almost use every element in the periodic table. And in the past, no one will trust you that you can bond 2 chip or bond 2 die together, stack 2 transistors on each other. And nowadays, it works very well. Okay, so treat this as something important, but not for the exam. I hope that, of course, you need to pass this class, but these 2 slides are actually more important than anything else we're going to teach, because they are the future. Okay, any questions? If no, then let's go